Example number 3, simplifying an algebraic expression. Okay, so not an equation, but an expression. So there are no equal signs, or one side is not equal to the other side. That's in the next example. Dun, dun, dun. Okay, sorry, example, let me start again. Example number 3, simplifying an algebraic expression involving factorial notation. Simplify where n is any natural number. So remember, natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to a bazillion, gazillion, quadrillion. Yes, those are real numbers, I promise. This is a little bit different than the example before, because we're talking about n's in general. Before we had actual numbers that we could hold on to, but this one right here is n's in general. So if I were to say n plus 3 and n minus 2, I'm hoping that you guys can see that these are consecutive numbers, meaning that they are 1 apart. So if I were to say something like n equals 5, this one would be n plus 3, which is 8, or 5 plus 3. And then this one right here would be n plus 2, 5 plus 7, 7 factorial. When you see it as numbers like this, I think it's pretty clear. 8 times 7 factorial. It's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is just the exact same thing as 8 factorial. So if we put what we know about the specific number case, let's talk about the more general number case. If we have two consecutive numbers, and the larger number is multiplied by the smaller number, but the factorial of that, we know that it becomes that larger number. So that was in the case of this one. 8 times 7 factorial just became 8 factorial. In the same way, n plus 3 times n plus 2 factorial is just going to be n plus 3 factorial. And done. Put a box around it. Okay, we can back away from the question because we're all done. This one is a little bit more tricky. So I'm just going to do, on the side here, I'm going to say, okay, so if we say n equals 5 again, okay, we say n plus 1 factorial, so 6 factorial over n minus 1, 4 factorial. The way that we can do this is we can we can expand the top one, so 6 times 5 times 4 factorial, and stop. Stop when we have a factorial that is helpful to cancel within the bottom. Bingo bango. So this answer right here is just going to be 30. Now this question in general is a little bit trickier, because we will not have a final answer of one specific number. But let's see what we do have. So if I have n plus 1, I want to expand it so that I have n minus 1 factorial to cancel within the bottom. So if I go n plus 1, the next one down would be minus 1. So n plus 1 minus 1 is just n. And then we subtract 2 from that original. So n plus 1 minus 2 is going to be n minus 1 factorial. Look at that. What we can do is we can cancel both the top and the bottom. And we have n plus 1 times n. What we're left with here is n squared plus n. Put a box around it, walk away from it, and we're done. However, in example 4, it becomes a little bit more tricky. So what we're doing is we're solving an equation. We're noticing that there is an equal sign and stuff, okay, expressions on either side of that equal sign. So we have to solve for n. We're going to do a very similar thing. We're going to use the methods that we learned in the above example, in example 3, to help us out with this one. Now, we're stating here n is an element of the integers. This is something different, so that can be negative, and they can be positive numbers as well, okay? And it does include 0. We know that factorials can only be natural numbers. So if we find a solution that's potentially negative, we're going to have to say that that cannot be a solution. You'll see what I mean in a moment. So n factorial over n minus 2 factorial equals 90. Going to use the same skills as we learned in the last video, in the last example. We're going to open up, we're going to expand this n factorial so that we have something that's helpful to cancel with in the denominator. So I would say n times n minus 1 times n minus 2. Oh, n minus n, that's confusing. That would be 0, folks, and that's not what we want. N minus 2 factorial. Now we stop at that point because we notice that in the denominator we have an n minus 2 factorial, so we can cancel with it. We don't want to forget that 90, okay? We don't want to drop that other side of the equation because it's an equation. It's important to have both sides. So I can cancel both the numerator and the denominator. And if I were to say n times n minus 1, I would say n squared minus n equals 90. Okay, so you're going to have to dust off some of that grade 11 pre-cal when it comes to factoring. Not much, okay, not much. Just a little bit. You want to set one side equal to 0 here, so we're going to subtract 90 from both sides. N squared minus n minus 90 equals 0. So we have to think of two numbers that multiply out to negative 90 and add up to negative n. We're going to get n minus 10 times n plus 9 equals 0. So that means when we're talking about the zero product theorem, n minus 10 equals 0, so n equals positive 10 and n equals negative 9. We must disregard this negative 9 because there's no such thing as negative 9 factorial. We can't have it. Okay, so so we know that our answer must be n equals 10. Another way that we can see that we must disregard this negative 9 is if we plug in this negative 9 into here, I would get negative 9 factorial on the top, which cannot happen, so automatically it doesn't work. But if we plug in this negative 9 here, negative 9 minus 2 factorial, we get negative 11 factorial. Sometimes when we substitute these numbers in, they'll work with one but not the other. It's important to go back to your original question and just see if both of these numbers can fit in. So n equals 10. Yeah, 10 factorial can be a thing, and 10 minus 2, so 8 factorial can also be a thing. So we know that n equals 10 is a good solution, whereas n equals negative 9 is not a solution.